Hello, everyone. Today, I would like to welcome my colleague and good friend, Jason Choi. Jason Choi is a PhD student at UC Berkeley, co-advised between Claire Tomlin and Kaushal Srinath. And Jason is now, I guess, a more senior PhD student and has been spending a lot of time exploring safe control, especially when you're trying to deal with practical, high-dimensional, scalable, adaptable, data-driven scenarios. And he has recently, I think that today he's going to be talking a bit about a recent work that he did in collaboration with his advisors, Melanie Zeilinger and Aaron Ames, comparing different approaches for safety filters for uncertain dynamical systems. Jason gave a guest lecture in my first round of this course, and his guest lecture is by far the most popular one that I've had. That was on an introduction to control barrier functions, and now has 24,000 views, and I still regularly get emails from people asking for follow-ups from him. And so I'm very excited to have him back to now talk to us about safety filters in general. And with that, please, Jason, take it away.
Yeah, thanks, Sylvia. That was a really nice introduction. Thank you so much, and thank you for having me again in your class, which is really exciting. So, yeah, today, like the last lecture I gave 3 years ago was more focused on like giving an introduction to control barrier function. But today, I think I want to talk more about a more like zoomed out view of safety filter design. Like, what are the overarching principles for all sorts of different methods for designing safety filters, and also like an extension of those design principles to data-driven approaches. So like the talk will be consisting of the control theoretic component and the data-driven component. I think the audience of this class, I don't have to spend too much time motivating why safety is important, but like this is just my short statement of why I want to work on like safety problems. So like working on robot autonomy is really exciting these days because you can see that a robot autonomy is achieving a lot of like cool tasks, like the videos the Boston Dynamics have. But I think like a crucial kind of gap that is missing, and I think this is the reason why we don't see a lot of robots around us until now, is that like the gap between what robot can achieve and what they can guarantee. So I'm not sure if this video already played, but to be fair, these videos are both quite outdated now, and like these video clips are just to kind of make my point. But like a lot of time people try like hard to make some task achieved, but then sometimes they can achieve it, or sometimes they cannot. Like sometimes they violate safety constraints. So these are like this gap between what they can do and what they are, like how they can reliably do things, are like the main impediment to the like success of robot autonomy. And I also work on like control or like flight autonomy problems with NASA these days, but there are like these new generation eVTOL vehicles which involve more like complicated aerodynamics because usually these vehicles have some changing configuration. Like they have like a vertical propeller when they take off, and then like this propeller tilts down when they like transition to like a cruise mode flight. And when these vehicles are pushed to their limits, or when they're much more vulnerable to failure, so and these kind of accidents do happen for these vehicles. So kind of guaranteeing safety for this vehicle is really, really important because they are really safety critical, and it costs a lot of money for the companies. So with that, like safety assurance for advanced robot autonomy, I think it still remains as an open problem. So this has been kind of my core research statement throughout my PhD year. There are many aspects of advanced robot autonomy. Today, I want to focus on two aspects of it. First one being complicated and uncertain dynamics of the robot. Like these days, robots are being more and more complicated. And the second component, the second aspect is that like the data-driven methods are like deployed more and more for decision-making of robot autonomy. So like data-driven methods, of course, are used already a lot for like perception, prediction, but they're also like being used for decision making. And also going to talk about why they have to be used for decision making later in my talk. So when we do incorporate these data-driven learning-based methods for decision making, how do we ensure safety becomes a really challenging problem? So these two aspects are the main aspects I want to focus on today. My talk will be consisting of two components. The first being control theoretic design. There will be no kind of data-driven components here. There are various methods proposed in the community to achieve safety, safe control design, including Hamilton-Jacobi reachability, control barrier function, predictive safety filters. I don't think I'll have enough time to cover all of them in a rigorous way, so I actually want to focus more on the outlook or like the kind of the overarching view of all these methods. This is based on the survey paper I wrote with Melanie's group and Professor Aaron's group. The second part will be like more introducing my research. So the research I've done by introducing the data-driven component to deal with the uncertain dynamics of the robot. So I'll talk a little bit about the GP-CBF SOCP safety filter. And I am going to spend a little bit more time on introducing my new work on the discriminating hyperplane-based safety filter. So that will be the kind of the last part of my talk, and then I'll like wrap up with some like key takeaways. So the first part of the talk will be control theoretic designs of safety filters. And again, this is a collaboration with Kim Webersich and Professor Melanie Zellinger from ETH and Andrew Taylor and Professor Aaron Ames from Caltech. So safety filter, like I guess I have to first explain about what safety filter is. And in Word, basically it's a module in the control system that filter out any unsafe action and only apply safe action to the real system. So there might be some other like module or like some other like logic or algorithm that determines what is the desired kind of control action that the robot wants to take. It can be like a learning-based policy. It can be some NPC controller. It can even be like a human kind of command. And the safety filter always like lies as the last layer of this decision-making kind of pipeline. And if that desired control is for some reason unsafe, it overrides it with a safe action. So that's kind of the role of the safety filter. I'm gonna just try to mathematically formulate what this filter does. So there are like three key objectives of this filter. And the first one is, because it is a filter, it tries to minimize deviation from the desired control. Because if the like override is kind of too conservative, or like if it overrides too much, it might deteriorate the performance objectives of the control. And definitely this is a very kind of critical issue with safety filter design. But that will not be like a main focus of today's kind of talk or today's lecture. My main focus will be more on how we ensure like the safety constraints. So this is the main role of the safety filter, which is to make sure that the state in all time satisfy the safety constraint specified by the designer. So this can be like a like a constraint because the robot doesn't want to collide to others, or like for flight vehicle, like a constraint because the vehicle doesn't want to lose its stability or things like that. And finally, the robot always have to take action that is always only physically feasible. So it has to select its action from a admissible control signal set. So these are the main component. And maybe one last comment about the safety filter is that, again, I'm not trying to propose this as like the single way of approaching safety problem, because in a lot of cases, actually, like performance objective and safety objective have to be considered together. But for the purpose of today's talk, where I want to focus on the safety problem, the safety filter gives us a nice framework where we can think about safety problem decoupled from performance. So that like the safety like filter definitely has some kind of way of minimizing its deviation from the performance goal, but still it prioritizes safety. So when we, by the way, I think I didn't mention it, but feel free to interrupt me if there's any question. And also feel free to, type in the chat. I'm gonna monitor the chat. So yeah, if you have any questions, feel free to interrupt me. Any questions so far? Right. So the next thing I want to discuss then is how we design these safety filters. And from kind of my point of view, there are fundamentally two problems when we design a safety filter. The first problem is verifying a set of safe states. So the main kind of issue here is that, like, let's say the designer gave you this safety specification, when the system is unsafe and when it is safe. So then, like, kind of the naive approach is that, as long as that set is given as the set large X, and the naive approach would be, whenever your set is not outside of this set X, you're safe. But actually, that's not the case, because there are some states inside state X, inside set X, that safety exiting the set X in the future is inevitable. So right now you're still inside this set X, but whatever you do, like however you do, you select the control action, at some point in the future, those states might lead you to the failure region. So the main kind of issue, so the main goal here has to rule out those states, has to be ruling out the states, and to come up with a subset of the target set X, which is denoted as S, that is verified to be safe. So that's the first problem. And then the second problem is then, once we verify this set, how do we achieve this through the control design? So it can be a control design, or it can be a constraint that is applied to the design of a constraint that is applied to the control input, which is more the case in safety filter design. So these are the two main building blocks for designing safety filter. On one hand, we have to verify the domain in which we can remain safe, and in the other hand, we want to select a control signal that achieves this. So kind of we'll think about safety filter design problem by kind of distinguishing these two problems. So what would be a good candidate for the safe set S is where the notion of invariance emerge. The set invariance is kind of the most fundamental principle to ensure safety and to design this safe set S. So I first basically give you a definition of forward invariance and control invariance and Nagumo's theorem. So forward invariant is defined for a closed loop system or an autonomous system where there's kind of no control, or the controller is already specified. So if there's a set S, and for all initial state inside the set S, if your trajectory stays indefinitely inside that set, then you can call that set a forward invariant set. So basically, the trajectory starting inside that set remains forever inside the set. And a nice way of verifying whether a given set is forward invariant or not is to check the boundary of the set. And when we check the boundary of the set, we'll get help from an implicit distance-like function that describes the set, which is called you can call it an implicit function, or you can call it a sign distance function. But basically, given this function h, the set S is described as a super zero level set of the function h. So let's say we are given this function h, then when we check the boundary and we check the derivative of h along our dynamics f, if this derivative is always greater or equal to 0 on the boundary, then because once the trajectory hits the boundary, because this derivative condition, immediately at the next time, the h has to be non-negative, which means the state will still be inside our super zero level set, which is our set S. So basically, that gives a principle that the trajectory will remain inside the set, So this could be a condition that we can use to verify whether a set is forward invariant or not. And this is called Nagumo's theorem in the literature. And this condition kind of is called Nagumo's condition. So actually, in the end part of my talk, I'll kind of come back to this condition. So it will be quite important throughout my talk. And also, like, as many of you who are already familiar with the concept of control variable function might know, this is also kind of very useful to define a CBF. Any questions about the forward invariance and Nagumo's condition?
Yeah, I have a question.
Yeah.
Yeah, so here we are defining s dot x greater than 0. So it is like exactly like in the CBF we used to define the s dot x less than 0, and like that we used to go ahead. So it is like opposite of that.
In the CBF, you define h dot smaller, like less than equal to 0.
Yeah, less than equal to 0, and hx has to be greater than 0, like that we defined like in the Lyapunov function similar way, the function we used to define for CBF. So it is like similar, or it is different thing?
It is similar. I'll cover the CBF, so maybe we can go back to this question. And like once I cover the CBF, I'll maybe get back to whether kind of you see the difference or like similarity. Would that be okay?
Sure. Thank you.
And we'll extend this notion to the control system. So now we are thinking about our system in an open loop fashion. So like we are kind of trying to select the control signal. And extension of the forward invariance concept to this control system is control invariance. So a set is called control invariant if for any initial state inside the set S, there exists a control input signal in the that is defined in the future. So that drives the trajectory to stay indefinitely inside the set S. So for all time greater or equal to 0, if your future trajectories can stay inside the set S, then this is called control invariant set. So like before we didn't have notion of control, so it was called deterministic notion. Here now the notion becomes like an existence. We introduce the existence of control signal to the invariance notion. And the Nagumo's condition can similarly be extended to this control system. Now, when you check the boundary condition, you can check whether a control signal exists that renders the lead derivative of h function to be non-negative. So if you can always find such control input at any point on the boundary, then basically the principle is that once the trajectory hits the boundary, you apply the control input that satisfies this condition, then it'll push the trajectory back into the set. So that's the way you can guarantee that the trajectory can stay inside the set. Okay, so that's like the notion of forward invariance and control invariance sets. So with that notion, just to recap how we would go about the design of safe controllers. So given this target safe set, we'll verify control invariance set contained in this set. And once we verify this control invariance set, we can design a safe controller so that under the closed loop dynamics, the set will be forward invariant. So just to kind of clarify the notion of control invariance and forward invariance. And like step 2 and step 3 can be like also kind of tackled together. Like you kind of verify invariance set together with safe controller. But yeah, like if you think about the open loop like system, then you kind of are trying to find this control invariance set. And then associated with that, you want to find like a safe controller so that under that closed loop system, your set becomes a forward invariant set. Okay, so now let's see how we can achieve this with Hamilton-Jacobi. And Silva, have you covered the reachability in your class? Great.
Yeah, but it doesn't hurt to have another person explain.
Yeah. So, but I'll be quite brief. So since you already covered this in the class, so in the reachability, there are many types of reachability problems, but now I'm kind of describing the specific type of reachability designed to verify like a maximal control invariance set contained in the target set. So the objective here is to avoid the failure region or the unsafe region for all prescribed future time horizon. And in order to do that, we will think about the notion of inevitable backward reachable set of this unsafe region. So here we set this failure region as our target set. And then we will, like this. And then we will compute the inevitable backward reachable tube, which captures all the state, no matter what control action you take, it will inevitably reach the failure region at some point in the future. So that the BRT will include all the states like that. And then the complement of that set will be called a viable kernel. And this is a viable kernel because by definition, inside this viable kernel, there will always exist a control signal that prevents you from exiting X, at least for the given time. So that's how you would compute this. That's what you want to compute. So you want to compute inevitable backward reachable tube of the failure region, and together you would compute this safe set. So this safe set is a finite time notion, and then if you extend t to infinity, then you would get the infinite horizon safe set, which becomes our maximal control invariance set. So these are actually how you do it. You define the value function of the optimal control problem, then you derive the dynamic programming principle of the value function. From that, you would derive the Hamilton-Jacobi PDE of the value function. So once you're able to solve this PDE, you're able to solve the value function, and as a result, the level set of the value function will characterize the BRT. And from that, if you verify your optimal control by evaluating the Hamiltonian, and this will give you the kind of optimal safety controller that kind of always push the state state away from the boundary, so that the V dot becomes greater or equal to 0. And to do this to get the maximal control invariance set, you run the computation for long enough until the value function converges. Then you would get the infinite horizon value function, and from there now you can get rid of the time notion, the time derivatives, and you can get a time invariant optimal control law. So once you have this optimal control law derived from the value function, the most vanilla thing you can do to design safety filter is basically whenever your value function is very, very close to 0, which means you're about to exit this viable kernel, you override your control action with the optimal reachability-based safety control. Otherwise, when you're strictly inside the set, you're further away from the boundary, basically you're allowed to do whatever you want, so you can just take you desire. So that's the most vanilla form of the reachability-based safety filter. I have an example here where I'm going to show how the reachability controller looks like. Any questions before that? Right. So here is just a very simple inverted pendulum example. We have an input bound, and we have a target safety constraint, which is basically constraining our angle to stay within some angle region around our equilibrium point. And let's say some user gave us a desired control input. So this is a bang-bang type of control for the first 6 seconds. And then after that, it will use some feedback validation controller to come back to the unstable equilibrium. And this bang-bang control will almost immediately kind of, push the system outside of our target safety constraint. So I think I have a simulation of that. Yeah, this is the initial state, and you can see that it quickly exit the target safety domain. The red boundary indicates the kind of the target safety boundary, which is our large set X. So for this example, let's see how we can do the reachability-based safety filter. I actually added some constraint to the theta dot when I compute the viable kernel. So here I'm not showing how I computed the viable kernel. I'm darkly showing you the result. But the dashed line is the boundary of the viable kernel of the targets that I use for the computation. So inside the dashed line is our maximal control invariance set. And starting from the initial state, whenever the trajectory hits the boundary of this invariant set, the reachability optimal control will kick in and then prevent it from exiting that set. So you see this kind of jump between desired control signal. The red lines are the desired control signal. The purple lines are the overrided control signal. So the reachability kind of kicks in whenever it's like kind of violating the safety, like trying to exit the boundary kernel. And it prevents the trajectory eventually from exiting the, the safety domain and successfully kind of converge back to the equilibrium point. So there are like two problems here. One is, I think you might have already learned, but reachability doesn't scale very well to higher dimensional system. So this is a simple like toy problem where you only have two states. So like reachability can be run quite quickly. Like, the offline computation doesn't take a lot of time. So for this example, for this toy example, it's fine. But if you want to scale this to more like complicated robots, it wouldn't work as easily like this. The other problem actually is more subtle, just that this kind of chattering control here, like, going back and forth between desired control signal and the optimal control signal, is actually not very, like practical. So like a lot of physical systems would not, you would not want to apply this type of control signal to those systems. Also, like the systems might have some delay, like oscillation, like this chattering might induce some unsafe behaviors that you haven't accounted for. So like, how would you apply or how would you intervene the desired control signal safely? It was actually a little bit of like open question in the reachability community, and that's also kind of the main motivation how the design principle of the control barrier function came out. So I'll move on to the CBF now. Any questions before that? Okay, so CBF, so now like CBF's main motivation is, rather than doing a hard stop at the boundary, like what we did in the reachability, we will try to smoothly break the trajectory as it approaches the boundary. And here now, like, I think we can go back to the question, like, we'll use some design principle inspired by the Lyapunov kind of stability condition. Because before, like if you recall the Nagumo kind of theorem, the Nagumo theorem only defines this hard stop when the trajectory actually hit the boundary. So the idea of CBF is even before we like hit the boundary, we would underbound our CBF evolution with some exponentially decaying curve, a smooth curve that approaches 0, so that if we ensure the trajectory to always stay above this exponentially decaying curve, then we can ensure that the CBF value always stay positive. And because of that, the trajectory will remain safe. So a CBF is defined as a continuously differentiable value function, such that I'll skip the minor details, but such that if this condition is met for all the state inside our invariant set or the super zero level set of the CBF, then we can ensure safety. And maybe I'll kind of go back to the question. So if we compare this to the Nagumo condition, in the Nagumo condition, we don't have this term. And in the CBF, we have this term. But the important thing is that at the boundary of the set S, or like this, at the boundary, the CBF value will be 0. So the Nagumo condition, like the CBF constraint becomes the Nagumo condition. And that actually proves why CBF would guarantee you safety. Did that answer your question?
Yeah, sure. Actually, the only thing I was talking about, like say here, the B X is starting at a positive value and slowly it is decreasing. So
Yeah.
over time, the slope of this function has to be negative. So I was talking about that.
Oh yeah, the slope of the function, yeah, in this case can be negative, and that's the main distinction between. So in the Nagumo condition, again, that's only defined at the boundary, right? So whatever the desired control does strictly inside the set, the derivative can be negative. In the CBF also, again, like since this minus gamma b, when the CBF value is strictly positive, this can become negative. So the CBF value, like the CBF derivative also can become negative. But in the reachability, the vanilla reachability, that was not the case. Like the vanilla reachability, the val function always, like the derivative of the val function always had to be non-negative according to our optimal control. So if we want to use our optimal control directly as our safety filter, that would induce some conservatism there.
Yeah, sure. Thank you.
Yeah. Okay. Yeah, I mean, it's just some terminology, but this part of the function which we use to design the underbound of the curve is called the comparison function. And this term, the constraint, like the terminology is not settled, I guess, in the community, but I usually call it like a barrier constraint. So the main theorem again is that under the control signal that satisfies this barrier constraint, the set will remain forward invariant. So all we have to ensure is the safe control input you apply satisfy this constraint. And proof again is Nagumo theorem. I'll skip this. And we'll think about control affine system for a while, for a minute, because for control affine system, we have a nice structure that the dynamics is affine in U. So if we think about the CBF constraint here, now like LFB and LGB are the lead derivative of B, according to our dynamics. These are, so LFB plus LGBU becomes the derivative of B along our trajectory. And this becomes linear in U. So when this becomes linear in U, we have a linear constraint. So as long as our objective function and our other constraints, our objective function is quadratic, and our other constraints are linear, we have a quadratic program. And even if our other like constraints are not linear, as long as they're convex, this becomes a convex program. So in general, like this can become, the safety filter can be formulated as a QP problem. And this is like quite a compact QP problem. Like there are not that many decision variables. Like the only decision variable is your control input U. So, you know, this is a QP problem that can be solved really fast online. And that kind of, you know, like this CBF QP design itself explains why CBF has been really, really popular these days, because the design of the safety filter is a really kind of, is made really easy. So, so this, but the caveat again is that this only works for control affine system. And if the constraint is not satisfied, you can just kind of relax the constraint in practice so that you don't have to worry too much about the invisibility. But the caveat is that if that invisibility may happen if your CBF design is wrong. So if your CBF design is rigorously validated, then that kind of shouldn't happen inside your safe set. So design step of the CBF would be you kind of design the CBF and you verify that the zero level set is control invariant, and also it is contained in your target safe set X. And then you choose like a gamma, or in general, you choose this comparison function you want to use to underbound the evolution of the contour barrier function, which will decide the profile of the smooth breaking. So the caveat here is that if the gamma is small, this becomes a more restrictive condition. If gamma is larger, then you will alleviate some conservatism, but then the breaking will kind of be more aggressive, like near, you know, towards the end when the trajectories are about to hit the boundary. So, so larger gamma is less restrictive, but it can be more myopic. I'll see what happens here. So here, I use a CBF that has this quadratic form, and again, this, you know, design, or this is like a very typical choice of CBF because we can kind of use Lyapunov-based principle to come up with this CBF. That's exactly what I did here, because the CBF, if you flip the sign of the CBF and you shift it, it's basically the quadratic Lyapunov function defined around the unstable equilibrium point. I'll skip how we derive the like specific values for this, but this design step has to be taken rigorously so that the resulting invariance set is valid. So this blue ellipse here, the the light blue ellipse is the boundary of the CBF zero level set, which is our safe set region S. And in this case, I'm showing you a trajectory under the CBF QP when I choose the gamma, the comparison function constant, to 0.2. And you can see that the filter like kind of smoothly intervenes the desired like control signal and then make sure that it doesn't hit the boundary. And you can see that the control signal is much smoother than the reachability-based control signal. And you can also see here that the CBF value is staying positive all the time. Now, when you choose a larger gamma, you can see the effect of gamma here now, because you can see that the value of the CBF now can become much closer to 0. It still doesn't allow it to hit exactly 0 because of the CBF constraint. But now the filter became much less restrictive. But like in some sense, it became a little bit more myopic because it like the filter kicks in, when the trajectory is very, very close to the boundary. So I think that's the CBF, and I'm gonna quickly move on to MPC. Any questions?
Yeah, you keep giving us this caveat of if the CBF is correct.
Yeah.
Can you comment on how difficult that may or may not be?
So I would say, so we could go back to the CBF condition, which is, so according to the definition, this has to be satisfied to be a valid CBF. So checking this condition when there's no control bound is not too hard because basically your value, your lead derivative, that the term that depends on your control input, as long as that term doesn't vanish, like as long as it's non-zero, you can take however big control input to satisfy this condition. So in the case there's no control bound, this is a little bit easier problem. In the case there is a control bound, this becomes a very difficult problem, and it almost becomes a reachability-like problem with control bound. Actually, so Sylvia and I and some other colleagues have worked on, like using the kind of reachability to design the CBF. But in general, I feel like it's still an open question. So there are like a lot of ongoing work, like trying to learn CBF or like, design CBF from data, or like there are really like a lot of, open like variety of methods that people are trying to design this CBF. So is there anything you want to add?
No, thanks.
All right, thanks. So MPC, I think I should maybe move fast. But so here MPC is basically we kind of work with a discrete time formulation. So first we discretize the dynamics, and then we formulate like a predictive control problem. And there are mainly 3 components here. So we have some desired control. Again, the desired objective is just to make sure we minimize the deviation from the desired control. But there are like 3 constraints. One is the target safety constraint, and which is obvious. We have the input bound, which is obvious. But the most non-obvious one here is the terminal set constraint. And this terminal set constraint is quite crucial for this predictive safety filter. So what is it doing? Let's see. So we will consider a terminal set denoted as ST, which is already designed to be control invariant. But the this control invariant set might not define the whole safe set domain. This might be just like a very conservative control invariant set, for example, around the equilibrium. And with this terminal set constraint, so after n step of the horizon, we always will make sure that the trajectory end up in that terminal set. Then what we can ensure is that once the trajectory end up in that control invariant set, since the terminal set is control invariant, it can stay inside that set forever. This is like kind of like a backup safety mechanism. So as long as the MPC solution is feasible, we know that there exists at least one trajectory that will indefinitely be safe. So that's why the terminal set condition, like the terminal set constraint, is a very, very crucial constraint that ensure safety of the predictive safety filter. And this feasible kind of sequence of U that can be determined by solving the MPC problem kind of serves as a backup plan for our safety mechanism. The last, and so again, we'll be very brief with the example, but here we will design this terminal set again with some Lyapunov-based terminal set. With that terminal set, when we start from the trajectory, we'll see that like and execute the predictive filter, we again can see that the trajectory never exits the unsafe set, and it like the MPC can even do a little bit better than reachability in the sense that it also kind of produces a smooth control action, and it guarantees safety. Now here, the thing I have to mention is that the prediction horizon matters a lot. So here we are, I think, using a prediction horizon where n is 20, and the dashed line basically show all the region where the MPC problem is feasible, and where the MPC problem is feasible is actually the safe set because of the existence of that backup safety maneuver. But you can see that as the time horizon gets shrink, the safe set will also shrink because your filter will become more myopic. So like you have now when you choose n equal 2, within 2 time step, your endpoint of the trajectory will always have to end up inside the target set, the terminal set. So in the MPC problem, like the horizon is the main design factor, as you can see here, and it would also definitely affect the kind of the safety property of the design. So to wrap up, again, since the fundamental 2 problems were the safe set design and the safe control design, so let's see the safe set comparison. Depending on what control method you use, you would end up having a different safe set representation. And usually reachability would give you the biggest safe set, but the MPC would also provide you a big enough safe set if the time horizon, if the prediction horizon is long enough. The caveat of the MPC is that safe set representation is not explicit. So you can only know once you solve an MPC problem, which is an optimization problem at a particular state, and check the feasibility of that problem. If that's feasible, then you're inside the safe set. If it's infeasible, then you're outside the safe set. So that's the safe set comparison. And the desired deviation from the desired control, you can see that, so this ideal desired control is something that we can compute in a trajectory optimization fashion. And all design mechanism like predictive filter, HA, like CBF, the deviation from the nominal control is quite much larger than what we could achieve ideally. But this ideal filter, you can kind of only do it in a very contrived setting if you know all the feature information of your desired control. So it's not very straightforward to achieve this ideal filter, but you can also see that this kind of, here you can clearly see that the safety filter would definitely affect the performance objective of the desired controllers. So I think that's the summary. That was the overview of each individual method. But I would say I would highlight like a key overarching kind of theme here. So first, reachability and CBF, they rely on some notion of surrogate function. And the surrogate function, maybe there is a question in the chat. So how was the goal defined for the MPC safety filter? How would it behave if the MPC goal ended up being in the unsafe set? And when you say goal, do you mean the terminal set?
Seems like the performance goal. Oh, no, never mind.
So the terminal set. Or
it seems to me like it's saying the goal for the system, is inside an unsafe set. What would happen?
Oh, I see. If the goal is inside the unsafe set, it means you cannot achieve the goal. Basically, the goal is wrong.
The goal could not be perfectly achieved, but is there a way this filter would behave in that case, a particular way?
So you mean like a goal point is somewhere, let's see. Sorry.
If I can rephrase my question,
Mhm.
if the design control policy is to let's say hit an obstacle, but
Mhm.
a safety filter would step in and try to avoid doing that, but it will also try to minimize the difference between the.
Oh, I see. Like a conflict between the constraint and the objective function.
Right.
But I would say if the constraint is like a hard constraint, the MPC would always prioritize the hard constraint. So like what I'm guessing would happen is like the trajectory will always try to stay, so close to the goal, but then it will like kind of prevent still from hitting that goal. Like similarly to what happens like here, like you see this the MPC trajectory sliding along this boundary. This boundary doesn't exist explicitly, but it just slides along this boundary, and this is determined by the feasibility of the MPC problem. Like the feasibility of the MPC says, if you're here, you can never exit this boundary. So I think something similar will happen, like that your trajectory would slide along like the viability kernel boundary that is close to the goal, like the neighboring to the goal, but you will never exit that goal. You will never exit the boundary.
I see. Okay, got it. Thank you.
Yep. Thanks. That was a good question. Okay. So the CBF and the reachability, basically both methods rely on some notion of surrogate function. And this is like a single scalar function that combines the information of our desired kind of safety constraint and the long-term effect of the dynamics. And usually this scalar function, the level provides the safe set verification. And it could often also provide like a measure of 2D safety margin, which is the case for CBF. And the gradient provides like the direction of the safety control, or like the direction to which the system can be more unsafe or like safe. So that is kind of the core concept of both the reachability value function and the control barrier function. And there's like a nice survey about, this unified view of safety filter design with the surrogate function. But the commonality of all three methods is basically the control invariance set. And I feel like I'm emphasizing this too many times, but again, in the reachability case, we are explicitly constructing the maximal control invariance set contained in our target set, like through the dynamic programming and by solving the Hamilton-Jacobi PDE. In the control barrier function, basically the design of the control barrier function is this process of finding the invariance set. And in the MPC case, designing of the terminal set and constraining the problem to have the terminal set constraint is to ensure that the trajectory always stay inside some control invariance set, albeit being that set being implicit. I saw the talk from last week. Is it last week, Sylvia? From Yushao Choi? Yeah. So I saw that he mentioned he kind of talked about backup CBF, and I would say backup CBF kind of unifies the control barrier function-based design principle and the MPC-based design principle really nicely, because the way he used this kind of backup invariance set is very, very similar to how the predictive filter used the terminal invariance set, the terminal set. So both methods, they have like this implicit notion of control invariance set. And kind of it actually can ease the control invariance set design problem a little bit. You don't have to explicitly find like a control invariance set anymore, but it does still rely on like a set like the terminal set. And the last point I want to make is that these all three methods now all are based on control theory and based on like a mathematical model of the system, the model-based control design. So when we start to think about uncertainty in the system dynamics, we have to make sure that this methods, all these methods work under those uncertainty. And for all these methods, for all three methods, they have an extension to robust formulation. So in the reachability, we extend this to differential gain between control and disturbance. The control barrier function, the control barrier function itself has some inherent stability notion, but it also there's like a notion of input to state safety, which makes the CBF level set with some additional margin to be still like control invariant under the disturbance. And finally, in the MPC, there's a technical constraint tightening that kind of add a margin to the constraint so that the effect of disturbance is addressed in the constraint design. So robust design to deal with model error is basically kind of the bridge from transitioning from like model-based design to like data-driven filter, or like to deal with system uncertainty. And that will be the second part of my talk. So how many time do you have? Like 30 minutes, maybe?
Yeah.
Yeah, okay. So, so model uncertainty, like, I guess, again, I don't have to spend too much time on the model uncertainty, but basically, I would say model uncertainty always exists for real-world system. Basically, because we always use some mathematical model we want to like we use to describe the system, but the actual system might have some discrepancy. So in the notation, we'll refer nominal model as with F tilde vector field and G tilde vector field, and we'll refer the true plant as F and G. So this mismatch between F tilde F and G tilde and G exists for most systems, and that would kind of break down the safety guarantee if we have designed the safety filter only with F tilde and G tilde. So actually, I'll show you an example here. So this is an experiment I've done for the GP-CBF SOCP safety filter. But when we designed the CBF QP filter, we used the mathematical model provided by the manufacturer of this cart pole. So which should be accurate, quite accurate. And in a lot of, for other objective, like for other like control design, like swing up behavior, like designing like a swing up controller, that mathematical model is kind of enough to achieve that. But when you actually visualize the trajectory in the phase portrait and see whether they exit the CBF 0 level set or not, like for all the 10 rollout we have experimented, they always exit the CBF 0 level set. So it means that this mathematical model is not perfect, or it doesn't describe the system dynamics accurately, and it results in this CBF guarantee failure. So we eventually kind of fixed this by introducing a data-driven component that learns how the uncertainty affects this safety constraint. So that's why we call this GP-CBF SOCP filter a model uncertainty-aware safety filter. And once we incorporate this data-driven component in our safety filter design, the trajectory will successfully always stay inside the CBF 0 level set. And this project is done with my collaborators Fernando and Wonsak and Bika. They're all from Professor Kaushu-Srinath's group. And also watch Armin's lecture, and he briefly introduced actually these SOCP filters. So I'll not spend too much time. Also, because since he gave a very nice introduction to Gaussian process regression, I'll also not spend too much time. But I'll just spend a time on where we applied the GP regression. So usually, like a lot of people use GP to model the uncertainty component of the dynamics directly. But here we did not do that. So here, let's see the CBF constraint. And the CBF constraint, there's this P dot term, which is the slope of the CBF along our dynamics. So it's LFB plus LGBU. But again, we don't have direct access to F and G, which is the true ground truth dynamics, the plant dynamics. So we only have model-based estimate. So in our actual filter design, instead of using ground truth B dot, we use B dot tilde, which is our model-based estimate. So there exists this discrepancy between the estimate and the ground truth value. the uncertainty term, which is the delta term here. And this delta term has this affine structure. So where we applied the GP is to learn this term, because this term basically explain how the uncertainty is affecting our safety. And we apply, from the data we collected from the experiments, we come up with a GP model to regress this uncertainty term in the safety constraint. And since Armin already provided a good overview of how GP regression is done, so I'll skip that part. But also, like, he gave a nice overview about this confidence bound property of the Gaussian process regression. We're exactly using that here as well to provide a probabilistic safety guarantee of the design filter. So basically, after we have this GP model, we replace the original constraint with the chance constraint, and we will represent this chance constraint with the using the confidence bound of the GP model. So we have a guarantee that the uncertainty term delta will stay within this bound, determined by the mean value, like the mean prediction of the GP and the variance of the regression. So the delta stays inside mu plus beta sigma and mu minus beta sigma with the probability of 1 minus delta. So it means the probability that our true derivative, Lie derivative of b dot, being greater or equal to b dot tilde, which is our model-based estimate, plus mu minus beta sigma, which is the worst case kind of bound of delta, will be greater or equal to 1 minus delta. So we'll, instead of b dot, now we can use this lower bound to kind of estimate this chance constraint. Yeah. And when we do that, just one more like technique we did is that since we know that the ground truth uncertainty term is control affine, we use a specific kernel structure that captures this affineness. And then when we do that, the mean term becomes affine in U, and the variance term becomes quadratic in U. So the mean term can be expressed like this, and the variance term can be expressed like this. And when we plug this expression into our constraint, the nice thing is that we maintain the convexity of the constraint. So now this is no longer a quadratic program, but this is a second order cone constraint. This becomes a second order cone constraint because of this specific structure we use. So that now this becomes a SOCP program, like SOCP, which is still a convex program, and it still can be solved really fast in real time. So this is the kind of gist of our filter design. And basically, I think I already showed you, so I'll just skip this. But like in the GP safety filter, once we incorporate this GP model and then replace our QP safety constraint, like the vanilla model-based QP safety constraint, with our second order cone program safety constraint, then we can successfully recover safety guarantee of the filter. Okay. Any questions? I think I moved a little bit too fast. So, but like the principle about how we use GP are already covered in the previous lecture. So here you can consider our work as application of that to our CBF-based safety filter design. So we did a more like rigorous analysis of when this filter is feasible or when this is not. If we go back to the CBF QP, the CBF QP always have to be feasible if the CBF is valid. But for the case of the SOCP filter, since we're learning the model uncertainty from data, and let's say we had the perfect knowledge of the uncertainty, which means our model, the data-driven model, can perfectly estimate the uncertainty term, which means the sigma term is 0. In that case, this will be, again, like a CBF QP, because we don't have the variance term here. And it will always be feasible. But now the problem with the SOCP filter is that this can become infeasible because of this sigma term, because the sigma term captures the the uncertainty of the prediction model itself. Like the prediction model might have some error, and that knowledge of error, basically how big the error can be, capture how much the data-driven model is uncertain. So if that error is too big, which means we don't have enough data or we don't have enough information to characterize the uncertainty accurately, so in that case, the sigma term can become really large. And that in that case, the SOC constraint can become infeasible. So that's why feasibility analysis of this constraint becomes really, really even more important than the vanilla like CBF filter. So the feasibility analysis basically trade off like from the feasible analysis, we can tell that the control input determined by this SOCP filter actually not only consider just safety, but it also consider what control action makes the GP model more certain, or what control action makes the GP model less certain based on the data that the GP model like use for inference. So it trades off between safety and uncertainty, and that's kind of a really kind of key principle how this SOCP filter works. And by doing a more theoretical analysis of this, we can actually use those analyses to design algorithm to do online deep learning, where it basically means we start with partial knowledge, or we can even start with zero data. And then like online, when we execute this filter, we measure how much the SOCP filter is uncertain about the dynamics and how the dynamics affect the safety constraint. And when it is uncertain, it can use the measure lambda to take an exploratory action, which is still safe, but will improve the knowledge of the system dynamics. And if we recursively do that, we can guarantee recursive feasibility of the system. So we did an extension of this GP SOCP filter to do this online learning. The other extension we did, and this is kind of, I just saw the question in the chat. I'll be happy to share the slides with Sylvia after the end of the lecture. So the second extension we did, and which is related to the inherent limitation of the GP regression, which is that it doesn't scale very well with the number of data. So Armin also discussed some of his work tackling this issue, but we also did some work tackling this issue because here we do a GP inference online, and the inference complexity scale proportionally to the square of the number of data. So if let's say the data is more than 10,000, like GP inference starts to really slow down a lot. So we improved the computational complexity of this by devising a very smart online data selection algorithm, and reduce that computational complexity to be only linearly dependent on the number of data points. And actually, the demo here I showed you is using that data, online data selection online, so that it can be executed in real time. So for more details of this, please refer to the papers listed below. And the main takeaway from this design is that what we did is basically making the vanilla model-based CBF filter adapted to the true dynamics uncertainty, and also robustify against the prediction error that the GP model can make. So with that two core component, we can guarantee the probabilistic safety. We can guarantee the safety of the filter at least probabilistically. Any questions in the GP filter?
No questions.
Okay, so I paced off a lot in the GP part because I knew that it could quite overlap with the previous lecture. But I'll slow down a little bit here now because I think this was the main part I wanted to highlight in today's lecture. So this is a recent work I done with undergrad student who just graduated from Berkeley last year, like last winter. Will. So Will and I are the co-first author of this work. And let's see what we did here. So I'll go back to the Nagumo condition, or like so-called Nagumo condition, which is the tangential characterization of control invariant set. So going back to this Nagumo condition, let's say we are given a function h, and we can verify that at the boundary of this set of the zero level set of the function h, we can always ensure that there exists a control signal that makes the h dot greater or equal to 0. Then we can ensure safety of the set, or like invariance of the set, right? So that was what was called Nagumo condition. So motivating question here is, do we need h here to actually design a safety filter, or can we do it without h? If there's any idea, of course, and you can see that my answer will be, you might not need h, but if there's any idea why we might not need h, yeah, like feel free to speak up. Sylvia, any guess you have?
Why you might not need H in general?
Yeah.
Well, I know why H can be difficult, but I mean, all you want from H is to know the set of allowable control actions.
Yeah. That's very good. That's actually exactly what I wanted to say. So H actually, when you think about Nagumo condition, it is not about H. It's about the allowable control action, and this condition doesn't depend on H. So it's a very geometric condition. I'll explain why. Another motivation is, like as Sylvia said, I think Sylvia touched on both points I wanted to highlight as a motivation. The certificate functions are, let's say there exist multiple candidate like certificate function that are valid. So I think a main caveat of certificate function based method is that you have so many freedom to choose certificate function you want to use. So I'll give you an example here. And this example is an example I worked with Sylvia before, but we had this example for one of our manuscripts, but then we end up not including this in our manuscript. So let's say we want to design a CBF. We characterized an invariant set, and we want to design a CBF filter. The blue level set here, the blue region here is the zero levels of the CBF. And let's say I pick this CBF here as my certificate function, and then apply the CBF QP for the trajectory. So the trajectory starts from here, and the UREF is the U desired control, which is intentionally designed to be unsafe, and it converges to the equilibrium point here, and then it converges back to the equilibrium point that was the starting point again. And so the desired control trajectory is not safe. And you can see that once we apply the CBF QP safety filter, the trajectory remains safely inside our CBF level set. So it works fine. It guarantees safety. Everything is good. Maybe we're done with our design. But let's see what happens if we choose a different CBF. Now they look quite similar, but the apex of the CBF is altered to a different location, which is at the origin now. So you can see that with the same gamma, with the safe set, you have a different trajectory behavior. So, and from the designer perspective, this is quite not intuitive, or this brings in a little bit of inconvenience, right? Because when you design a safety filter, by designing the constraint, you want to make sure your system behave in a certain way. We can see that by just changing the circuit function a little bit, you can have a very different behavior. So here, you can see that the trajectory can stay quite close to the boundary on the left. Oh, sorry, boundary in the right. But the trajectories are not allowed to stay close to the boundary on the left. Here, I intentionally choose the CBF, design the CBF to be symmetric. So you have a more like mirror symmetric behavior on this boundary and this boundary. So this, like, to me, it seemed really a little bit weird that, and basically the question here was, or the my lesson here was that, like, certificate function design might be a quite underdetermined problem. And also, this is not a specific problem for CBF. This is also a problem for reachability, because reachability, depending on what distance function you choose, distance-like function you choose, that is used as your target function and used as a boundary condition for the Hamilton-Jacobi PDE, you will also get different value function. And from different value function, you will also get different control behavior. So going back to Nagumo's condition, the key insight was that this Nagumo condition actually doesn't depend on the choice of H. Because if you look into the control input space, this is describing a very kind of geometric condition. So this cone that I'm using, like the cone in the pictogram is visualizing all possible direction of the vector field by choosing different choice of U. And H dot greater or equal to 0 basically means your U should direct into the set. So for control affine system, this H dot greater or equal to 0 is a linear constraint, right? And this becomes kind of hyperplane-like constraint in the control input space. So let's say you have a control bound like this, U. And then if you apply Nagumo condition, then you're basically cutting off or like splitting the control input space to two different subspace, one being where the control action can be unsafe, and where the other part where the control actions are safe. So basically what we did is define this as a discriminative hyperplane, but also the Nagumo condition only applies to boundary, right? So we can kind of extend the notion of discriminative hyperplane to like the entire state space. But basically the hyperplane discriminate the control input space to safe and unsafe control input actions. And such hyperplane exists always for control affine system. And the informal kind of theorem with this hyperplane is that this hyperplane, as long as the control input satisfy the this hyperplane constraint, this serves as a sufficient condition for Nagumo condition at the boundary of the control invariance set, and thus it can be provided as a safe control law. So the key feature is that this is a quite natural extension of Nagumo's condition to the interior of the set. And this also generalized the Hamilton-Jacobi reachability and CBF basic control law for control affine system. So you can think of reachability-based control law and CBF-based control law as a special instantiation of this A and B like values. So A in the reachability is determined by the value function. In the CBF, A is determined by the CBF. And like B in the CBF, you have this comparison function that determines the B. In the reachability, you have 0 in the place of B. So the nice thing is that now you kind of have this a little bit more generalized definition. When you design the safety filter, you don't have to rely on any notion of like certificate function. And this can be worked together with any types of safe set representation, like any way you want to represent your control invariance set. You can use this discriminant hyperplane principle to design your safety filter or like the safety constraint for the filter. And in the paper, we specifically proposed two methods, one being the supervised learning and the other being the RL. I'm not going to the detail of this because of the time, but the supervised learning has one limitation that it requires pre-verified control invariance set to produce a supervised training labels. But the RL discriminant hyperplane doesn't need that. So we'll now quickly show some examples how where we applied the DH filter, and then I'll wrap up. But here, so in the cartpole experiment, we again manually designed the invariance set. So this is not coming from like reachability or CBF. We just manually designed it and verified through Monte-Carlo simulation that this could be a valid control invariance set. And then we use it for supervised training of the discriminative hyperplane. And the RL, we didn't need this invariance set, and we just ran the kind of modified PPO algorithm to train the filter. But now with this DH filter, when you are trying to train a new task, now you're applying this filter to train like a task policy, like learning like a task policy. Basically, the same filter can be applied to like every task. So we have like 3 tasks. And if you compare it to the vanilla algorithm we used was the PPO. And if you compare it to the PPO, like the PPO, of course, violate safety a lot. So in the first row, we show the performance, and in the second row, we show the safety violation. And you can see that vanilla PPO violates safety a lot during the training. And of course, this is because PPO doesn't consider safety. But PPO Lagrangian, which is one of the state-of-the-art safe RL method, still does violate safety often. With the supervised learning safety filter, when you apply to PPO, we had 0 like constraint violation. And with the RL like DH filter, we still have a slight violation, which means that the RL DH filter is not like perfect. Like it's not very rigorous because it's still like a learning-based safety filter, but it successfully mitigates safety much better than the PPO Lagrangian. But the more important thing is that this the RLDH filter is not task specific, whereas the PPO Lagrangian method blends safety and performance together. So the resulting safe behavior becomes quite task specific. So I'll skip this part, but the final experiment I want to show is the application of this to half cheetah, where the kind of dynamics is actually like really more black box. So the PPO, when we apply this to just vanilla PPO to learn robot, maximizing its travel distance, PPO learns to like run quite aggressively, but in a lot of cases, the robot falls forward and then violates safety constraint. Here, the safety constraint is the robot's head not hitting the ground. And the PPO Lagrangian, when the training is done successfully, it learns to walk really conservatively. So it compromises the performance a lot, but it does achieve, very good kind of safety performance, like the safety. But like again, it's not very ideal because the learned behavior is really conservative. It's not something you want to. It's not like the behavior that maximizes the performance. Now, when we apply the RLDH filter to the PPO, you can see that the agents are still running quite aggressively. But then when at the instance that was about to, fall forward, the RLDH filter kicks in, and then it prevents the robot from falling forward. So this kind of is a demo where like showing RLDH not deteriorating the performance of the task that much, and still like successfully mitigating safety. So like the main message here is that the discriminative hyperplane is an abstraction of the safety constraint for a control-affine system, which generalizes a lot of existing methods. I think, we just try to conceptualize this to be very general, and then came up with a learning-based method to learn this safety filter directly without relying too much on the control search gate functions. So there are like that was the end of my main part. Sylvia, I guess you're already out of time, right?
We are. So anybody who needs to leave is welcome to leave.
Yeah.
But Jason, if you're willing to stay a couple minutes, that would be great.
I'll be staying around if you have more questions. I'll just end my talk with these key takeaways. I'll not walk through this, but I'll just leave it here, and then I'll let you guys go. If you have any questions, I'll stay here.
So well, first, thank you so much, Jason, before I jump right in. So the discriminating hyperplane thing, does it just strictly generalize everything for control affine systems, or are there situations in which you would want to use a certificate function still?
So what the remark we had in the paper, and I also have that remark here, is that I think certificate functions are still useful for like verifying the set. So again, this goes back to the two problem, right? We have the safety set verification problem, and then we have the constraint design problem. So what we wanted to tackle was the second part, like which is when we design the constraint, we might not have to rely on certificate function. That was kind of the main motivation. But I think certificate functions are still useful to verify the safe set. Yeah.
So can you showed a non-smooth control invariant set for that last example.
Yeah.
So in general, is that not a problem for when you're using discriminated hyperplanes in the same way that's a problem for the control barrier functions?
A good question. I am not sure. So at least from our result, it was not a problem. But again, this was more like we didn't look too much into the mathematical properties of the filter yet. But when the main theorem we had was proven mathematically rigorously, the main requirement in this theorem is that the hyperplane parameter, which is ax and bx, they have to be Lipschitz continuous in X. So with that, I think we have the guarantee that the feedback control will be Lipschitz continuous. So we don't have any issue. Whether the smoothness or like a non-smooth of the invariance set affect how they would affect the Lipschitz continuity of this A and B, we have to investigate more. Yeah, that part is not fully investigated yet.
Okay, interesting. Thanks. Other questions from the audience? Okay, then I'll let people go since it's past time. But thank you so much, Jason. And yeah, it looks like we already have requests for the slides. So if you could send me those, and then we'll also.
Yeah, thank you again for having me, Sylvia, and I hope you all have a great day.
Bye.